Dear students, in chemical bonding chapter, we are going to the next concept. Before that, I will put a small question on you. If you are considering your favorite atom, that is carbon, okay? So carbon, you are writing somewhat like this, correct now? And its atomic number is 6. And if you are writing the electronic configuration, it is 1s2, 2s2, and 2p2, correct now? So when you consider here, this S2 is completely filled, 1s2 is completely filled, 2s2 is completely filled, and now remaining is 2p2. So 2p can be written as 2px1, 2py1, and 2pz. Nothing will be there. But when you consider the molecule of carbon like methane, CH4 you are writing, it's having 4 valency. But here there is only 2 orbitals which is there present here with unpaired electrons. Correct now? So that is the question comes over here. Why this carbon, even though it's having only 2 electrons at the outermost, but it is ready to make 4 bonds, or it combines with 4 elements, and it's having valency 4. Why it is like that? So for that answer, we will go for the next concept that is called hybridization. You can see here, hybridization. Clear? So what do you mean by hybridization? So hybridization is nothing but a mixing of orbitals of comparatively equal energy, to form entirely new orbitals of equivalent energy is called hybridization. That means many atomic orbitals of comparable energy combines. Okay, so here you can see atomic orbitals of comparably equal energy to form entirely new orbitals of equivalent energy is called hybridization. So we will discuss with example, and with respect to your syllabus, the example is with respect to carbon. Carbon shows, right now in front of you, carbon shows 3 types of hybridization. One is sp3 hybridization, another one is sp2 hybridization, and third one is sp hybridization. Let us discuss the first one, that is called sp3 hybridization in carbon. sp3 hybridization in carbon. Atomic number of carbon is 6, correct? Just now we discussed that. Its electronic configuration is 1s2, 2s2, 2p2. In excited state, what do you mean by excited state? Whenever any other element coming near to carbon, any other element, hydrogen coming near to carbon, oxygen coming near to carbon, if any other element coming near to carbon, the carbon undergoes excited state. So what is that excited state? Let us see here. An excited state, electron from s orbital jumps to p orbital, and then its electronic configuration will be 1s2, 2s1, 2p3. Hope you got it. Otherwise we will discuss this, how it is. See, let us see here. Here it is S2. From this S2, one electron jumps to P2, 2p2. And you are getting this excited state electronic configuration as 1s2, 2s1. Why it is 2s1? Because the electron from 2s2 jumped into P. That is why it is 2p3 now. Okay, so this is the thing. So if we are coming to the next line, that is the valence electronic configuration is represented as, how do you represent the valence electronic configuration? That is 1s2, okay, 1s2, 2s1, okay, 2s1, 2p3. How do you write? You are splitting into 2px1, 2py1, and 2pz1. Clear? If you are not getting it, let us discuss once again. See here, what happened is, from P, there are 3 orientation, px, py, as well as pz. Correct? Okay. So, with respect to that, you are splitting this electron as 1, 1, 1 like that. So, last line we are going to this. Okay. So, what does this line says? It says that, okay, hybridization of 2s. Hybridization means mixing. Just now we discussed the definition of hybridization, mixing of atomic orbitals of comparable energy or equal energy. So here 2s, 2px, 2py, 2pz takes place to give a new sp3 hybridized orbital of carbon. So before going to that, let us discuss one example here itself. See, you have 4 pens. 4 pens are there. Okay, so when it is hybridized, I am mixing it all together. you have one peak, second peak, third peak, and fourth peak. The next line is completely hybridized. So like this, you are getting 4 peaks over here. Let us represent with respect to carbon. This is with respect to pen. Okay. So let us with respect to carbon, we are coming to see. You can see on board somewhat like this. See here, 2s1 s orbital, 2px1, 2py1, 2pz1. Correct? So when it is hybridized, you can see 4 sp3 orbitals are mixing over here. When it is mixed, you are getting the sp3 hybridized carbon. Its structure is tetrahedral geometry, and you can see here how they are represented. So 1, 2, 3, 4 orbitals are there, and they are also having the same type of energy. There is no any change in energy levels. So that is an example for sp3 hybridization with respect to carbon. Other examples are, okay, methane molecule and ethane molecule are there, that we will discuss in depth in next. Okay, so here it is the representation of a carbon atom with sp3 hybridization. Let us go for the next, that is sp hybridization. Same thing we are discussing over here. Nothing is different. See, sp2 hybridization, we are taking carbon into consideration. Atomic number of carbon is 6. Electronic configuration, you know that 2s1, correct? Correct? 2s2, very good. 2s2, 2s2, and 2p2, 1s2, 2s2, and a 2p2. So when you are coming to the next, that is when the electron jumps from s orbital to p orbital, you are writing 2s2, 1s2, 2s1, and 2p3. So if you are coming over here, the valence electronic configuration, okay, so it is represented as 1s2, 2s1, 2px1, 2py1, 2pz1. This thing I think already we discussed it in the sp3 hybridization. But what happens to here? Here the things happening is in a different way. That is, this 2s1 as well as 2px1, 2py1. These three is involved in hybridization, whereas 2pz1 is not involved in hybridization. Clear? So let us discuss with respect to pen. Okay, here I will take this as the 2pz1 is not involved in hybridization. Others are involved in hybridization. Other three are involved in hybridization. And this is not at all involved in hybridization. Now we are counting the peaks. 1, 2, 3, 4, 5 are there. Because this one, 2pz1, is not involved. Correct? That is why you are getting like this representation. Now we will discuss with respect to carbon, how it is. Okay, let us go for that. Okay. See here, when it is hybridized, we discussed that when it is hybridization takes place, the thing happening is 2pz1 is not involved in hybridization. So let us take that one into consideration. Here you can see one s orbital. This is px, py, pz. Pz I rounded it. We rounded it because that orbital is not involved in hybridization. So these three are undergoes hybridization. It's not involved as such. You are writing it, drawing that. See, you can see the carbon is 2pz is as like it is. Other three are here itself. So you have 1, 2, 3, 4, 5 nodes are there. So it is called sp2 hybridized carbon. Example is ethene, boron trichloride, all these things. We will discuss it. Okay, next we will go for the next, that is called sp hybridization. Up to here the things are same. Whatever here, things are same. That is atomic number of carbon 6, and excited state you are writing it as 1s2, 2s1, 2p3, and in valence electronic configuration you are writing it as px1, py1, pz1. So things happening over here is different. What's happening over here? Here the things happening is somewhat like this. 2s and 2px is involved, whereas these 2py and 2pz is not involved in hybridization. In pen, if you are representing somewhat like this. So these two are involved in hybridization. If you are taking, you can see only 2 knobs. It's involved in hybridization. These two are not involved in hybridization. Like that we are right. So when you count, you can count here. You can count here as 1, 2, 3, 4, 5, 6. 6 knobs are there with respect to pen. But with respect to carbon, how do we represent it? Let us see here. Okay. Okay, we'll come back to the notes, our notes. Okay, see here you can see a beautiful representation of carbon which is undergone sp hybridization. That means here this s orbital px is involved, whereas py and pz is not at all involved in hybridization. What happens here? See, you are getting this type of representation. This is not involved, py is not involved, complete diagram is here. And another one is your pz is not involved, you can see complete, and other is px and s orbitals are as such itself. So you have here this much of nodes. So that is the representation of sp3, sp2 and sp orbitals. Let us go for the next, that is example. Example of or salient features of hybridization. By going through this, you can come to a conclusion that what are the salient features of this hybridization. Orbitals with almost equal energy will take part in the hybridization. When you are doing hybridization process, only the type of substances which are having atomic orbitals of equal energy is involved in a hybridization. That is the first point. Only with respect to equal energy is involved. So whatever the number of hybrid orbitals produced, whatever the norms you are getting, that is with respect to the number of atomic orbitals involved. See here, they are having equal energy. We are writing it's having equal energy you are getting. Number of hybrid orbitals, whatever the number of hybrid orbitals produced, that is equal to number of atomic orbitals involved or mixed. Next one is geometry or shape. Shape of any type of hybridization depend on the type of hybridization. So geometry or shape of a covalent molecule can be indicated by the type of hybridization. sp3 is a tetrahedral. sp we are coming, that is a linear structure, like that. Structure is changes. The hybrid orbitals are more effective in forming stable bonds. Due to hybridization, carbon makes whatever the molecule the carbon makes due to hybridization, they are highly stable in nature. So that's about the salient features of the hybridization. Okay, so let us go for the next point. That is, what are the necessary conditions for hybridization? To make an hybridization, what are the perfect conditions? The conditions are the orbitals of valence shell take part in hybridization. Whenever you are considering any type of hybridization, inner orbital not at all involves. Valence shell orbitals are involved in a hybridization. Orbitals involved in hybridization should have almost equal energy. What type of electron will be involved in hybridization? Not inner orbital, valence shell orbitals. So what is the energy? That is should be equal energy. Promotion of electron is not a necessary condition prior to hybridization. Every time the promotion of electron is not the condition, but whenever it depends on the atomic orbitals coming near to carbon. Okay. In some cases, filled orbitals of valence shell also take part in hybridization. Filled electron will also take part in hybridization. That is called valence shell electron repulsion theory. In that, we will discuss the fourth point. So these are the points or conditions for hybridization. One is a valence shell electron involved. Second one is the equal energy. Third one is it's not always necessary that the electrons will jump, because sometimes the filled valence electron shell is also involved in hybridization. So let us go for the examples. The example given in your syllabus is nothing but hybridization for that is methane molecule. Let us come for this beautiful molecule, that is methane molecule. So up to this level, you know this because we discussed this in the hybridization part. So there is nothing but in methane molecule there exists a carbon and 4 hydrogen. So whenever you are writing the molecular formula of methane, okay, it contains 4 hydrogen. CH4, here we written over here, it's a CH4. So 4 hydrogen. So let us discuss with respect to carbon. Carbon atomic number 6. So its electronic configuration 1s2, 2s2, 2p2. Then in excited state it is 1s2, 2s1, 2px1, 2py1 and 2pz1. Up to here it comes, valence configuration. Hybridization of a 2s, 2px, 2py, 2pz takes place to give a new sp3 hybridized orbitals of carbon as follows. I think up to here we discussed in hybridization part. So you are getting the production of sp3 tetrahedral carbon. You are getting this. This one is we discussed. So you are getting this. And this diagram, this color, I'm just changing in the next part. That is, whenever considering any methane molecule, The one sp3 hybridized carbon combines with one sp3. You have only one carbon in methane. So one sp3 hybridized carbon, this sp3 hybridized carbon, the color I changed it somewhat like this I represented here. Okay, combines with the four 1s1 orbitals of hydrogen. Hydrogen's electronic configuration is 1s1. So hydrogen's structure is given over here. Okay, that is 4 you are taking into consideration. Okay, and results in the formation of a methane molecule. See here, the shape is tetrahedral and bond angle is 109 degree 5 minutes or 109.5 degree, 109 degree 28 minutes. So we are writing it as 109.5 degree. So let us see here, 4 sp3 hybridized orbitals of carbon is here and 4 hydrogen. When this combines, overlapping takes place, means hydrogen comes near to this, one hydrogen comes here, one hydrogen comes here. When this combines, you are getting the molecule. See, this is carbon in the middle. You can see here carbon in the middle, hydrogen, 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 hydrogen. So you can see the diagram here, hydrogen in all the sides. Okay, hydrogen, hydrogen. Okay, so so when you are coming over here, the structure is like this, and angle between it. So here skeleton structure is at 109 degree 28 minutes or 109.5 degree, like that you can write. So this is the way how you represent the structure of methane with respect to hybridization. Hope you got it. If you have any doubts, you are always welcome. So we are going to the next point. That is, next one is nothing but the one more example, that is ethane. We discussed methane, we are discussing ethane. So how it is formed over here? That is, you are taking 2 carbons, which is sp3 hybridized. So let us draw that diagram so that you can get an idea. So we are taking here 2. This is the result. I will write the starting. So this is 1 carbon. Okay, and you have how many hydrogens? 6 hydrogen. 6 hydrogen you are writing. Plus again one more carbon. It is hybridized something like this. Okay. So when these two are combined, you can write, see here, this is overlapping with this. That is given over here. This is the overlapping of this. And this is your beautiful sigma bond. You can write. And next, here one hydrogen. We'll take different color for it. Hydrogen accommodates. Okay, hydrogen accommodates. Here one hydrogen. Here also one hydrogen. Okay. Here also one hydrogen. Here it's already undergone. Okay, see here one hydrogen, here one hydrogen. These are all sigma bonds. This is also sigma bond. So you have 3 plus 3 plus 1, 7 sigma bonds are there. See here, hydrogen, 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 hydrogen. Again, 109 degree 28 minutes is the angle. You can see it. If it is not visible, you can see it here. Structure. You can see. Correct now? So if you are writing propane, you can also write for propane, butane, like that you can write. But here, these are the 2 examples for you. sp3 hybridization. So next we are going to sp hybridization on ethene molecule. Ethene, it's a molecular formula. You know that 2 carbons are present and 4 hydrogens are present. When you are writing electronic configuration of carbon, we are discussing about carbon right now, 1s2, 2s2, 2p2. So in excited state it is 1s2, 2s1, 2p3. Valence electronic configuration 1s2, 2s1, 2px1, 2py1, 2pz1. In case of hybridization part, we discussed that this s orbital, p or px and py is involved in a hybridization, whereas others are not involved. So how do you got it? We already going back to the same diagram, that is 1 s orbital, 2 p orbitals, and this is not involved. And finally, you are getting 1, 2, 3, 4, 5 peaks are there. That's called sp2 hybridized orbitals of carbon. Clear? So that is the sp2 hybridized orbital of carbon. Okay. So let us come here. If you are coming over here, you are having 2 sp2 hybridized carbon and you have 4 hydrogen. Okay. So what happens here? See here, this we will discuss. See, this is sp2 hybridized carbon and this is not involved in bond formation. What happens is these two forms a bond called pi bond. And these 2 bonds, these are overlaps sideways and you are getting this type of bond. That is nothing but a sigma bond. This is pi bond, sideways overlapping. And here you have hydrogen and hydrogen. Here also hydrogen and hydrogen. So you have 1, 2 hydrogen, third hydrogen here, and fourth hydrogen here. So you can see here 4 hydrogens. So this is representation. What happened over here is, see, this is undergoes pi bond. Upper part is undergoes pi bond. Okay, so this is undergoes pi bond. So if we take this structure into consideration, actually how it is happened. So let us draw that once again. See here, this is involved. Okay, this one I am writing. This is pz orbital. Okay, and another one is like this. So like this. And to this you combined with the hydrogen, correct? So here hydrogen 1, 2, 3, 4. And whatever the middle part is there, this is the middle part one. So that is not involved, but it undergoes hybridization like this. So this is called pi bond. Clear? Or you can also draw like this overlapping, or downwards overlapping also you can represent. Downward overlapping also you can represent. See how you represent the downward overlapping. Let us see that. See, downward overlapping is like this. Either from the top or from the bottom. Okay, or from the bottom. Hope we discussed in the previous class with respect to oxygen molecule. Just I will go for that, recall that oxygen molecule and come back over here. So this is nothing but a carbon-carbon. That is a pi bond. Okay, then this black is pi bond. If you take other things, okay, that is red, okay, that is sigma bond. Again here sigma bond with hydrogen, sigma bond with hydrogen, sigma bond with hydrogen, and sigma bond with the hydrogen. So how many sigma bonds are there? 5 sigma bond and 1 pi bond. Pi bond is this one. This is pi bond. 1 pi. Hope you got it. I will recall the things that we discussed in the previous class about oxygen. Okay, so that is somewhere here. Okay. Okay, here we discussed about oxygen molecule in the previous class. That is, pi bond takes place either from the upper part or from the bottom part. You are writing it. This one is pi bond or this is pi bond. So pi bond is from the top or from the bottom. These things we discussed in the previous class for your understanding purpose. So I recalled it. Okay. So now we are going for the next, that is our acetylene or ethane molecule, triple bond. We discussed here about double bond. Now we are coming to the triple bond. Up to here, valence electronic configuration is represented as so and so. You know it. And this one also you know it because we discussed these things in hybridization. Okay, you can see here hybridization 2s 2px takes place. These two takes place hybridization, whereas these two is not involved. So you are writing it as such itself. When in case of acetylene or ethane molecule C2H2, it is 2 carbons having this type of hybridization. We have taken over here 2 carbons. Okay, same 2 carbons undergone sp hybridization and 2 hydrogen here. And what happens? One hydrogen comes over here and another hydrogen comes over here. These two combines together, you are getting a sigma bond here, and this sidewise overlapping takes place between pz and pz and here also. So as a result, you have triple bond here. One is due to sigma bond, other two are pi bond, and the bond angle is 180 degree. So that's about the hybridization of the carbon molecules. Okay, so another one is BSEPR theory that we'll discuss afterwards. So these are the examples that are present in your syllabus. So try to understand all these things and write a question whatever you are getting with respect to this and send to me. Okay, or you can put it as an assignment and please put it in front of me and discuss all the points. And next class we will discuss about IIT chapter, whatever the questions you are getting, medicine based questions, whatever it may be, we will discuss in the next class. Okay, right now if you have any doubt, you can ask here. We will solve it.